Okay, yeah, stay safe out in the rain and everything. So we're talking about, we left off talking about the naive Bayes classifier, sorry. And the idea here is we want to find, what is the probability that our observation belongs to class C, okay? And so we say, the probability that our new observation belongs to class C, given our data, kind of given the given our data and the training data. Okay, this is equal, and using Bayes' rule is it's the probability of getting our data x new given for that particular class C, given our training data and given our training data, multiplied by the prior probabilities of belonging to class C, given our training data, divided by, and then this is basically the total probability of all of this stuff, okay? Is everything glitching out again?
A little.
A little? Is it livable? A little? All right, so I wanted to demonstrate what this looks like in practice, okay? Week 6 Friday. It's already Friday of week 6. I feel like I say this every single class, but because every time I'm always amazed. Okay, so anyway, we're gonna we'll try this out in practice, okay? In practice, okay. Well, and before that, the naive Bayes assumption, as far as the naive part goes, the naive part is that our x variables are independent. Okay? Because they probably aren't. A lot of times your x variables have some kind of covariance or correlation between them, but we're going to naively assume that they are independent, and then we'll see how this works, okay? All right, so we'll take a look at the good old IRIS data set, all right? It's such a good data set. It's like the classic data set. Okay, so we've got 3 classes, 50 observations in each of these 3 classes, and then we have 4 numeric variables that we can use to try to figure out here. Okay, so we can just do iris sepal length. Oops. Let's just create a simple plot. We'll do iris sepal length, iris. You know what? I don't know. Well, all right. Let's load up ggplot. Larger variable ggplot2. Okay, and then we'll do ggplot iris, and then we'll map x to be sepal dot. I forgot. Is length capitalized? I need to know the names. Names of iris. Sepal.length, yeah, okay. So ggplot, we'll look at our iris data set. Our aesthetic mapping will be x will be sepal.length, y will be sepal.width, and then we'll add geom underscore point, and the color or the fill will be species. Does this work? No. No, maybe I have to. I do the mapping here. Fill will be species. Okay, sorry. Or color?
Yeah.
It's color, okay. Color, all right. Okay, so there we go. This is what we have on when we look at sepal length and sepal width, and then we can kind of just change these to petal dot length and see, can we kind of make different clusters here, or not clusters, things. And so, if we were just doing a two-dimensional thing, we would create there would be a normal model centered here, a multivariate normal model centered here, a multivariate normal model centered over here, and a multivariate normal model centered over here. Now, when we look at this, we see that sepal length and petal length are correlated, and a better classifier would include that correlation, and we would have. So let me just kind of copy this plot. Yeah, that's fine. Okay. If we were going to use normal models, okay, when we draw them, so if we assume they're uncorrelated, our normal model contours look something like this, okay? If they were correlated, we would be able to do, we would, so here being uncorrelated, we would get a plot that looks something like this, all right? Okay, but if we did something correlated, then we would try to do something like this, right? This is obviously better than having them having our whatever the axes of our multivariate normal would be this. Okay, so this would require us to estimate the covariance. Okay, this assumes the covariance is 0, or that is x's are independent. Okay. But if we did things that are independent, it's not going to be as great, but still pretty useful, right? Okay, so let's just kind of see what this could look like in practice. So in practice, so what I'm going to do is I'm going to take our iris data set, and I'm going to select, with the iris data set we have 50 observations of each of the 3 species, and I'm going to select 40 of each of them, okay? And so I'm going to say training rows, sample 1 through 50, and choose 40 out of those. Sample 51 through 100, choose 40 out of those. Sample 101 through 150, choose 40 out of those, okay? And then we'll subset training to the training rows, and then testing will be everything that's not the training rows, right? So here I've got training and testing, and then the 3 species that we have are Setosa, versicolor, and virginica, and then and here we go. We're gonna we have a few options for the class conditionals, which is this part, the x new given that it belongs to a class. Okay, this is a class conditional. This is the probability of getting our x observations given the class. Okay, so probability of x given class C, okay, and our training data. Okay. For this, I'm going to just use maximum likelihood estimation for a normal distribution. Okay. And then and because we're assuming independence, I can just estimate the mean and variance of each of the 4 variables separately, right? I don't have to try to estimate the entire variance covariance matrix for all 4 variances because we're assuming they're all independent. Okay, so here we're going to use maximum likelihood estimation to kind of specify our class conditionals. And so the maximum likelihood estimate for the mean is just the mean of the sample. And then the maximum likelihood estimate for the standard deviation is the unadjusted standard deviation of the sample. Okay, so that means, normally when you take variance, you divide by n minus 1, and then you take the square root of that for your standard deviation. In this case, we're going to divide by n rather than n minus 1. And so here I'm going to create a function called population standard deviation and population variance. And so when you run variance in R, it always uses n minus 1. So I'm just going to multiply that by n minus 1 and then divide by n. There's no option in R for a uncorrected variance thing. So anyway, I create a new population variance function, and population standard deviation is just the square root of the population variance. Okay, and so I can just kind of test this out. The variance of the values 1, 2, 3, 4 is 1.6666, whereas the population variance is 1.25. So, if you take the squared distances from the mean, and then you divide by 3, you get this, and if you divide by 4, you get that. Okay, and then likewise, the standard deviations reflect that as well. Okay, so I'm going to just kind of summarize all of these things. So using dplyr, I'm going to take our training data, right? This is what we're using. We're using our training data, and we're going to say we're going to group by the classes. So we've got three classes, 3 species. So we'll group by the species, and then we'll summarize it. And I'm going to say the mean of sepal length is going to be mean of sepal length. Standard deviation of sepal length using the population standard deviation formula or function that we just created will be that. So these are going to give us the maximum likelihood estimates of the sepal length, the mean and the standard deviations of our 4 variables. So that's what we have here. Okay. So let me just print this out. MLE estimates. So these are the mean and standard deviation for each of the 4 variables for the 3 different species that we have. Okay. So far so good with everybody? Yeah? Okay. And then, we could say, well, if we wanted to just look at setosa, we can do that. And if we wanted to just look at, let's say, sepal length, okay, I can just say select the columns that end with SL for sepal length, or SW, or petal length, or petal width, and things like this, right? So we want so this is what we have. Okay, so let's when we go to our testing data, right? We have 30 observations here, and let's just kind of look at the first row. Okay, so here we got 5.4, 3.9, 1.7, 0.4. All right. And so I'm going to just take this first value, 5.4, and this will be my x for sepal length. Okay. And we know that the answer is setosa, but we'll try this out. Okay. So my x.sl is 5.4. All right. And so the way the Bayes classifier works is we're going to say, okay, well, that's our x, and we're going to calculate what is the probability of x given each of these different classes and their respective estimates. So let me just kind of print out MLE estimates for the first 3 columns, which have the mean and the standard deviation of our sepal length, which is what this variable is, right? So I'm going to say, okay, calculate the probability and we're assuming a normal distribution, so we're going to say calculate the probability of getting this value 5.4 if I assume the mean to be 4.93 and the standard deviation to be 0.33. So I'm just using the maximum likelihood estimates. So when I do that, it says, okay, the probability of that is 0.444. Then I say, okay, well, what's the probability if I used the mean and standard deviation for the versicolor class, right? And I do that, and it says, okay, the probability of that is 0.468. And then what's the probability for the Virginica class, right? And we get this, 0.112457, all right? So looking only at that first one, that's each of these for each of the three different classes, right? Right now, our prior probabilities on the class, we can just take how many, in our training data, we have 40 from each species, right? So our prior probabilities, without looking at the data, what's the probability that we have it from each class? Each class has the same probability, so we would say the prior probabilities will be 1/3 for each class. Okay, and here we've got the probabilities for each of these. So in the denominator, okay, so the denominator is going to basically be d norm, and our observation was 5.4. Whoops. Given basically the mu estimate of sepal length and the standard deviation for sepal length for class 1, right? For class 1, class 2, okay? And then we multiply it by the prior probability, which is 1/3, okay? And then we do this for the same thing for class 2. I'm sorry, this is class 1, okay, for class 2, and then we do the same thing for class 3. So my denominator is going to be each of these things multiplied by 1/3 added up, okay? So I can take this and I would just multiply this by 1/3, and then I would add this times 1/3, and I would add this times 1/3. Okay, and so this is what's going to go into my denominator. If I run that, my denominator will be 0.34183, right? So I can just say this will be my denominator. And then in the numerator, it's basically just each of these for each of the different classes, right? It's for the probability that T nu is whatever, Virginica would be, you know, the D norm, our observation 5.4 times mu underscore SL for Virginica, and standard deviation underscore SL for Virginica times 1/3, right? So basically, the numerator for, I forgot my levels already, the levels of species. So I can do numerator for Setosa, and then I would have numerator for versicolor and numerator for Virginica for each of these things. And it's just each term right here. Given our maximum likelihood estimates. So I have my numerators, and then therefore I can just do the numerator divided by the denominator, and this would be my class probability based on this one variable alone. So our denominator, okay. So currently we have a 40, based on this, you know, our probability of being in each class is given by this, right? So based on just that one value, 5.4 that we have, you know, we would probably estimate it to be versicolor, okay? But this is just taking into one variable into account. We want to do all four, and we're going to assume that all four are independent of each other, right? So we would basically just have to expand this. So we would do dnorm, not just the first variable, but we would also look at the second, the third, and the fourth variable, right? And so we would look at the first row and now the second variable, okay? And this is going to be the sepal width. And I would do sepal width for all of this, and then I have to change all of my, look at my maximum likelihood estimates again. And I would just copy this value and plug that in right there. Copy this value, put that in right there. Copy this value, put that in right there. Okay, and then so you can see this is just kind of like manual method, right? So here, if I just use these two to try to classify this, this is what we would get. Okay, and then whoops. Okay, and we would get different probabilities here, and then so taking into account the second one, now we have a very strong favoring towards the first class. Okay, and then so therefore, if I just take into the account the first two variables, I would multiply this and this. Okay. So the this part, whoops, this top part, x nu given t class, this can be expanded into just the product of basically d norm for each x variable. Okay, d norm of our observation given the class. Okay, and so I would do d norm for the sepal length times d norm of the sepal width. Okay, and then I would multiply that by 1/3, and then on the bottom I would divide it. Okay, so this would be the probability after two variables, and then I could expand that to all four variables. All right, conceptually, does this make sense? What's going on? Okay, and so that's basically it. All right, so this was kind of like manual method. I know I just assigned homework 3, but so for homework 4, this is a small preview of kind of where we're headed. Is obviously you don't want to have to be continually copying and pasting your maximum likelihood estimates from the data into your Bayes classifier calculator, right? So homework 4 will be to try to create create a function that will classify your observations accordingly. Okay, and so I'm writing up homework 4 so you can do this, but I just want to make sure that conceptually we understand what we have to do manually, right? Because if we don't understand what we're doing manually first, then there's no way we can program, write a script or program to do it for us in an automated fashion. So the manual process of calculating the probability of our observation, kind of given our maximum likelihood estimates for each class, you multiply those across the top, and then you divide in the denominator basically the sum of all of those probabilities at the bottom. Is that okay? Any questions? We're good? Okay, so that's the naive Bayes classifier. The naive part is that we just multiply our normal densities together, whereas in reality we would probably want a multivariate normal distribution, which reduces this to this only when the x's are independent. Okay, so that is the probabilistic classifier. The book talks a little bit more about some other things. There's logistic regression and Gaussian processes. The Gaussian process, and they spend like 1 page on it. We can have an entire lecture dedicated to that, but we're not gonna do that. Okay. Now I want to talk about a non-probabilistic classifier, and this one is called the k-nearest neighbors classifier. Okay. Okay. So conceptually, the k-nearest neighbors classifier is quite easy to understand. Okay, so all we have to do is let me just copy this image. Okay, so with the k-nearest neighbors is you have your data, right? And then you get a new test point, okay? So I'm going to just put in, let's say an x, let's say I put an x right here, okay? If this is my test point, I draw a circle centered at x, okay? Until I get a certain number k observations inside my circle, okay? So let's say, x is my test point, okay? And then I draw a circle around x. So there are k observations in the circle. Okay, and then I count how many, I count to which classes they belong, right? So here I've got 1, 2, 3, 4, 5, 6 observations. So in this example, I've got 6 observations, and all 6 are green. So therefore, x will be classified as green. Okay, let's say I put a dot right here. Okay, here I draw a circle, so I would get 6 observations. Let's see, or I probably want 7 observations. 1, 2. Okay. Well, anyway. Okay. So now I have 7 observations, but okay. So here I have 7 observations, okay, and 5 are blue and 2 are green, okay, so x is classified as green. Okay, I mean not green, x is classified as blue. Okay, so basically you're calculating, your 6 closest neighbors, your 7 closest neighbors, whatever you have, and then you just say, okay, well, which classes do these belong to, and then whichever has the most there, that is how you classify your data point. That's it. That's really it. Okay, and so well, here I'm drawing circles. Drawing circles is basically finding and finding the circles is here I'm using the Euclidean distance, right? But there are other ways to measure distance, right? So so circles show all the points with the same Euclidean distance. Okay, but there are other options, right? You guys have learned about like L1 and L2 norms, or no? Kinda. Okay. So Euclidean distance. This is known as our L2 norm. Basically, like if you have some vector v, and then they do this to kind of show the norm of, is it one? What is it? Now I'm messing up my notation, but basically this is basically the Euclidean distance, right? You just you take each x component and then you square them, and that gives you your kind of the magnitude there. The L1 norm draws basically a diamond. Okay, you get a diamond around the. So rather than circles, you get. It's imagine you're playing a like an old school. I don't know. You're playing like a board game or something, and you can either walk forward or you can walk to the right, and you're limited to you get to walk 5 spaces on your turn, right? And you're not allowed to walk diagonal. So therefore, the area that you can kind of all the distances that you can reach are either going to be 5 up, 5 to the right, or some combination of 4, 1, 3, 2, 2, 3. Or 1, 4, something so that your x's and your x and your y add up to something. So that's what we have here. Okay, so this would be kind of your L1 norm. Here it's the absolute value of basically x1 plus the absolute value of x2 must equal some kind of constant. And then over here you have basically x1 squared plus x2 squared equals some kind of constant. Okay, and so that is the k nearest neighbors, and obviously you can expand this to higher dimensions. Okay, and choosing a larger or smaller k will either make your decision boundaries much more wiggly or smooth. Okay, so choosing the k. Okay, so smaller k's will create decision boundaries that are more wiggly. More wiggly, you are more prone to overfitting. If k is too small. Okay. So you can imagine if I have this thing, and I do, if I just say k is equal to 1, right? So the extreme case, k is equal to 1, we're going to get basically between every 2 points that are slightly different colors. It's here. Let's. This is too small for us to be any good. Is right here? I don't know if let me zoom in just on this one portion right here. Okay, where's this? So let's just copy this, and we'll. I don't know if you guys can see this. All right. So if I just do k equals 1, then you get we run into a little bit of problems, right? Because if I have a data point right here, the closest observation, I don't know if you guys can see, this one is green and not blue. And so this one, its closest observation, everything kind of between here, here, and wherever this is closer than either of these points, so kind of something like this, everything inside here is going to get classified as green. Okay, even though most likely it should probably all be classified as blue. Okay, and so you get kind of this weird boundary between every single one of these points to try to accommodate for k equals 1, right? So extreme case, k is equal to 1. The algorithm will find the nearest point, and whatever nearest point that is, it's going to say that's the class. Okay. Use that to classify your new observation. Sorry. Okay. And on the other hand, if k is huge, then your boundaries can get messed up. Okay, if k is huge, then it's possible, like in the extreme case, if k is bigger than any one particular class, then you can get situations where things don't get assigned at all. So let's say, well, this is not a good example, but yeah, you're going to lose a lot of information, especially if so if, I'll just say, okay, if k is huge, you may miss important ways to distinguish between classes. Okay, and there's we don't have an easy way to choose a k, right? So you can do some cross-validation by and testing out different values of k and seeing which one produces the least amount of error. Okay, so we can try to decide on the best k by using cross-validation. Okay, and so the way cross-validation works would be, so your training data, whatever data you have, your training data gets further split into kind of a training and testing set. Okay, right? Training data gets further split. Quote, train and test. And then you, using whatever k that you have, okay, so use a k here, and then test its performance over here. Okay, and then try a different split, right? So do a different split. Okay, and then use a new k. Use a k for the training, and test its performance on the testing. And test the performance over here. Okay. And then by doing this several times, you get an idea of kind of your error classification rate for different values of k. Okay, so repeat this process and to get an idea of your performance, your misclassification performance for different values of k. All right, we'll end here, and then and I guess next week. So there's Monday is a holiday, so I'll see you guys on Wednesday. And on Wednesday, I guess we can look at this some code to see how this works as well. Okay, have a good weekend. Stay safe in the rain and storms and all of that.